come up to the final transform derivation expression, which is the Laplace of e raised to negative at sine bt u of t. To prove that the said Laplace equation is equal to its complex frequency domain b all over s plus a squared plus b squared, we are going to derive that equation. So the Laplace of e raised to negative 80 sine bt is equal to the integration of e raised to negative st times e raised to negative 80 sine bt dt as 0 approaches infinity. Since the two expressions or functions have the same basis, using a power rule, we will have an equation of e raised to quantity s minus a t sine dt, wherein 0 approaches infinity, or it is still equal to e raised to negative s plus a t sine bt dt as 0 approaches infinity. Considering these two expressions or functions, we will use integration by parts, wherein the values of u is u, du, dv, and v are as follows: sine bt, b cosine bt dt, e raised to negative s plus a dt, negative 1 all over quantity s plus a, e raised to negative quantity s plus a, respectively. Plugging in these values, we will have an expression of negative e raised to negative quantity s plus at sine bt all over s plus t, as which has limits of 0 to infinity, minus the integration of negative b cosine dt e raised to negative quantity s plus a dt all over s plus a as 0 approaches infinity. Evaluating this expression, we will have the following expression or functions are which is 0 minus negative 0 plus b all over quantity s plus a times the integration of cosine bt e raised to negative quantity s plus a dt as 0 approaches infinity. Canceling this value, we will have a final answer of b is equal to quantity s plus a times the integration of cosine bt e raised to the negative quantity s plus a dt. s plus at dt. Considering cosine bt e raised to the negative quantity s plus at, we will again repeat the use of integration by parts. Given u is equal to cosine bt, du is equal to negative b sine bt, dv equals e raised to negative quantity s plus at dt, and v is equal to negative 1 all over s plus a e raised to the negative quantity s plus a t. Plugging in again these values, we will have this expression, wherein b is equal to, b all over s plus a times the quantity negative cosine bte raised to negative quantity s plus a t all over s plus t minus negative b all over s plus a times the integration of sine bt e raised to the negative quantity s plus a t dt, 0 as 0 approaches infinity. Now, after coming up to this expression, we will now let e raised to negative 80 sine bt equal to y. Using that variable, we will have an expression of y is equal to b all over s plus a times the quantity of negative 0 minus negative 1 all over sa minus b all over quantity s plus a plus 1. Using the LCD, or finding the LCD of this said expression, or this said expression, we will have an answer of b all over s plus a times the quantity 1 all over s plus a minus b all over quantity s plus a times y. Doing a distributive property, wherein this one, we will have an answer for y of which is equal to b all over quantity s plus a squared minus b squared all over the quantity of s plus a squared times y. Transposing the value of y to the other side, we will have y all over y times the quantity s plus a squared plus b squared all over the quantity of s plus a squared, which is equal to b all over quantity s plus a squared. Since y is equal to the Laplace of e raised to negative 80 sine bt, we have now proven that the Laplace of e raised to negative 80 sine bt is equal to b all over sine plus b all over s quantity s plus a squared plus b squared. Rock.